Today I'm going to talk about MPI, Multiple Perspective Attack Investigation with Semantic Aware Execution Partitioning. My name is Shiqing Ma. I'm from Purdue University. This is a joint work with Zhai from Nanjing University, my colleague Hyung Li from University of Georgia, and my advisors Xiangyu Zhang and Dongyan. So the context of our work is about attack investigation. A traditional attack investigation has two components. The first one is a provenance tracking system. A provenance tracking system records all the system-level events involving all the system objects and the system subjects. For example, this one shows a very simple log. The line 2 shows that the process 24 receives a packet from the socket 0, and line 3 shows that the same process writes some data to the local file taskman. Once an attack simpleton event is detected, we perform backward or forward analysis on the provenance data and to try to get the causality graph. From the two log events, we get a causal graph like this. Each node in this graph represents the system object, like files or socket, and a system subject, like processes, like process 24. So once an attack is detected, and we can actually generate the causal graph, we can easily understand all the system objects and the system subjects that are related to the attack. This one shows a real-world example of the generated causal graph. As you can see, the graph is quite big. It has many nodes and edges. It's very complex, and also it's very hard for the analyzers to investigate. The main reason is because of the dependency explosion problem. So in traditional provenance analysis, we have an assumption. So one write event will actually depend on all the read events that happen before this write event. This is obviously not true, and also it will introduce many bogus dependencies into the causal graph. Researchers have proposed many solutions to this problem, including execution partitioning. So the basic idea of execution partitioning is to partition a long-running process into multiple execution units. So the dependency model will be changed. All the events happen within one unit will be thought to be causally related, and all the events happen in different units are thought to be independent. Also, units can be connected in the causal graph through the inner unit dependence. We will give a concrete example here. Imagine you are using Firefox. You visited many websites, and eventually you download one file. If we follow the original assumption, the downloaded file will actually depend on all the sockets, depends on all the websites we have actually visited. But this is obviously not true. The downloaded file perhaps only depends on one socket. By applying the partitioning technique, we will make Firefox to be multiple execution units, and each unit will just handle one socket. The downloaded file will be correctly attributed to the socket. Now let's look at some of the existing execution partitioning techniques. State-of-the-art execution partitioning technique is called BEEP. It's an event loop-based partitioning technique. One iteration in the event handling loop will be considered as one execution unit. Here is an example of the event handling loop. So it basically fetches one event from the user input or program internal events, and then it will process the event. BEEP will instrument the event handling loop. As the entry point, it generates a unit enter event, and at the end of the loop, it will have a unit exit event, and all the events happen between those two events will be considered belong to the same execution unit. We have been using BEEP for a long time, and we have learned many lessons while using BEEP. So the first one is BEEP generates very low-level information. For example, mouse clicks and keystrokes. Those are all external events but they will trigger the event hunting loop. However, the mouse click, you may have many events, but they don't directly map to the user actions, like keystrokes. When I type the URL, I have many keystrokes, but it's just one user intention. The second problem is BEEP requires training for inter-unit dependence and dependence detection. So users will have to generate hundreds to thousands test cases and use the pin tool to actually monitor all the memory accesses and try to detect the memory dependence across units. This is a very heavy process. The third one is actually BEEP generates many useless events. For example, the mouse movement events. Those events actually do not contribute to any causality information. After notifying these problems, we also identify what is the desired system we want. So first of all, we want to partition the program with some meaningful information. For example, we want to partition Firefox into tabs. So whenever you see the graph, you actually know the node in the graph represents a Firefox tab or Firefox web page. The second one is we want to give some flexibilities about the causality model. For example, it can be a Firefox web page or can be Firefox page. This will give the users multiple perspectives to investigate the attack. In the later, we will show an example demonstrating the advantage of using different perspectives. Also, we want to get rid of the heavy training process. And third, we want to have as less units as possible, drop all the necessary units. This will help us reduce the runtime overhead caused by the unnecessary instrumentation. Here is an overview of MPI. MPI is inspired by the process isolation mechanism in operating systems. The basic idea of MPI is to partition the execution based on user-defined high-level data structures, and we call these data structures tasks. If you partition the program according to different tasks, you can have different perspectives to analyze the program and analyze the attack. For example, for Firefox, we always use tabs and web pages, and also you can use the sessions or windows, etc. This is a basic workflow of MPI. First, the programmer will have to annotate the source code. This is actually to inject your intention, investigation intention, the perspective into the program. And with the annotated source code, we will use the LLVM with our customized passes to compile the annotated code and generate the executables. Those executables will actively expose the task information into the provenance system. Also, we developed another Annotation Miner, which helps the programmers to annotate the source code. Let's first look at what are the annotations we have in MPI. As mentioned before, MPI is inspired by the operating system process isolation mechanism. So we first review the operating system process model. First of all, in OS, one process can be uniquely identified by its process ID. When a scheduler chooses a new process to run, it will update the current value in the kernel and start to run the new process. Processes can exchange data between each other. This is an IPC mechanism like pipes. Similarly, applications organize their works in a similar way. It's just a different task in this concept. So similar to the PID, we need an indicator annotation to indicate which task it is, to differentiate itself from other instances. Also, we need another indicator variable to indicate the context switch within this application. So when you are switching from task 1 to task 2, you need to update this variable, and we know you are having a new task. And also, tasks can exchange data between each other, and this is Similar to the IPCs, we use another annotation channel to annotate such variables, such data exchange channels. This is a real example of Vim, how we annotate Vim. So in Vim, you can open multiple buffers, editing different files in Vim. And each buffer is represented by the buff_t data structure. Each buff_t can be uniquely identified by its ID. So its ID, so the task is about the buffer, and the identifier will be the buffer ID. Also, Vim has a global variable called curBuff. It's of the type buff_t. It's pointing to the current buffer the user is editing. So this variable will be served as the indicator variable. When this value is changed, the user must have moved to another buffer. And Vim also has its built-in clipboard system. So the users can copy, cut contents from one buffer and paste it to another one. The channel, this data structure is the Yank register. So this variable is annotated with the channel annotation. With the annotated source code, our LLVM path will automatically find all the redefinition points of the indicator variable and expose the task information to the low-level provenance system. In this case, do command will actually switch to a new buffer, and the curBuff value is changed. So here, we instrument the code after curBuff, after this definition. And first, we test if this is really a new buffer, and if so, we expose the current ID to the low-level provenance system. For different provenance systems, we use different mechanisms to expose the task ID. For Linux Audit system, we use queue system call with illegal parameters. As we said before, tasks can be represented by data structures, just like buff_t in Vim. And we develop another annotation miner to help developers find such annotations. Our annotation miner will help the developers find the data structure that corresponds to the task. And we use differential analysis to do this. First, we design a test A. For Vim, use Vim as an example. We first open a file, do some editing, and then save it. At runtime, we'll collect the number of instances for each data structure. For example, in this case, we just use one buffer, so buff_t has one instance, and post_t also has one. And then we use another test. In this test, we duplicate the workload, but in two different buffers. So test B actually do the same thing twice in two different buffers. And at runtime, we also collect the same information, all the number of instances for each data structure. Then we merge the results. As you can see, some of the results are task-related, like the buff_t data structure. Because test B actually duplicates twice the workload in test A, the number of instances in test B will be twice the number of instances in test A if the data structure is buffer-related. For other cases like log, you can only have one log buffer in one program. No matter how many buffers you have, it will always be one. And then we can select our candidates. For those candidates, we also have many candidates, but our approach is actually to select the top-level data structure, because if the data structure contains other data structures, if the top-level data structure has two instances, the sub-data structure also will have two instances. In this case, post_t is removed because it's just one field of buff_t, and buff_t will be recommended to the user. Next, we'll talk about the thread model in MPI. This is a very simple Firefox case. So Firefox first sends DNS requests to DNS threads, And when it starts to load the content, it needs to create sockets and will send requests to the sockets process. So those DNS thread and socket thread are known as worker thread. They don't really have the global context. They don't know which tab is serving. So when you cannot accurately contribute the events happening in the worker threads to the global context. To solve this problem, we introduce another annotation called delegator. So we add one more field in the delegators and inherit the task, global task identifier from the top level data structures. This is an example of how we annotate Firefox. So in Firefox, when the main thread wants to call the socket thread for socket connection and the data communication, it will send one NSConnect event to the socket thread. So this NSConnect event will be annotated as a delegator. So when it's created, we instrument the code to get the global current global task ID, so that when the event is eventually dispatched to the socket thread will still know the global context. Now let's just show some evaluation results. First, we show the number of annotations we have in MPI. The first column is the name of the application, and then we measure the size of the programs by line of code. Those 4 columns show the annotations we have. For most of the programs, we have less than 10 annotations. And the last column shows the number of instrumentations. It's automatically done by LLVM pass. As we can see, we have a few hundreds to thousands instrumentations. This indicates it's not possible by manual instrumentation. Firefox has a maximum number of annotations and instrumentations. It requires about 36 annotations, but we think it's still acceptable. As we discussed before, we need to tell the task information to the low-level provenance system. We will use additional system events, so this will cause some space overhead. For this table shows the space overhead we measured on 2 different provenance systems. The first one is a Linux Audit system, and the other one is HiFi. For each application, we just use the most intuitive perspective. As we can see here, for some applications like Firefox, the number of additional events generated by MPI is far less than the one generated by using BEEP. This is because Firefox has many internal events, and just like the mouse clicks. And for other programs like Bash, the results are actually very similar. This is because for Bash, the event handling loop is dealing with each command. It is already a high-level user intention. So this one shows the runtime overhead caused by the instrumentation in MPI. We can see for all the programs, the runtime overhead is less than 1%. This is because first, we just have a few instrumented instructions in the application. And even though we have a few hundred to 1,000 instrumented points, but comparing with the original size of the program, it's still very small. Now we will show one case study of using MPI. It's a very simple scenario. So we first use Firefox, visits a few websites, and then during browsing, we actually download a few torrent files as well as some normal files. At last, we will download those torrents with the transmission program. If we use the traditional approach, we'll get a graph similar like this. So as we can see, there are many sockets and files here, mainly introduced by those 2 processes. If we use BEEP, we'll get a graph like this. This graph actually only shows the Firefox part. Because Firefox has many internal events, this graph actually will contain a lot of Firefox nodes and make the investigation very difficult. Here we will show using MPI to partition Firefox with a tab perspective and partition the transmission program with each input torrent file. It basically mimics the user behavior actually. First, we search on Bing and we open many web pages in different tabs. Those are the search results. And in those websites, we can download some files, including torrent files. And those torrent files will be downloaded by the transmission program. It doesn't have any bogus dependence. And the graph is pretty small, but also very accurate. This is another example of using MPI to partition Firefox by different websites and use the MPI to partition transmission by the user by input torrent files. This is the final generated graph. As you can see here, the difference with the previous one is the soft home web page. Previously, we visited this website in multiple different types, but with a different perspective, the website perspective, we can actually merge all those nodes into one. This graph actually is more clear, telling us the source of the downloaded torrent files. MPI is related to many works, including general provenance systems. Many people spend like a few decades in this area to have very low overhead and very low space overhead and runtime overhead provenance systems in the operating system level. And it's also related to the log storage and integrity research areas. MPI is still not a perfect solution. It has some limitations. First, it requires a source code because this is a LLVM-based solution. And second, it requires annotations from the programmers. We already provided an annotation miner to help the program to annotate the source code, but still it's not an automated solution yet. And annotation miner currently only finds the data structures, like the buff-t data structure. Actually, in the program, we need indicator and identifier annotations. Those are for variables instead of data structures. So, as a conclusion, we propose MPI, an execution partitioning technique based on high-level data structures. It allows the user to annotate the data structures corresponding to these tasks and leverage compiler to instrument the operations of the data structure in order to capture the unit context switches and delegations. We implemented a prototype, and our evaluation results show that MPI generates very small and accurate graphs with very low overhead. And it also supports multi-perspective semantic-aware attack investigation. Thank you.
We again have plenty of time for questions.
Claudio, Oracle. Is the source code available?
Not yet.
Just, a remark that basically it's very hard to convince someone that annotating software with a third-party annotation without having the source code, it's kind of a risk in many big enterprises.
So if I understand your question correctly, you mean if the source code is not available, how we do this, right?
Yeah, something like that.
So this is, thank you for asking this question. This will actually complete our discussion. So currently, MPI only works with programs with source code. But for others like malwares especially, they don't have source code. We have other solutions like BEEP. It's basically binary based. There are other alternative solutions. And for malware, the dependency analysis, there are some differences from normal programs. First, malwares usually are just short-living programs because they want to keep a low profile. They don't want to, pop up on your desktop or something. So the dependency in the malware is actually small. So that's one part. And the second one, we actually can analyze the related events with this malware. For example, the activities it has and the source of the malware. For example, just like downloading from Firefox. So this will also help identify the whole attack instead of just one malware itself. So we still think our technique can actually help about the attack investigation.
Okay, thanks.
Thank you.
Well, actually, I'd also like to ask you a question.
Okay.
I'm curious, in this process, I think it's awesome that you have the Annotation Miner to help the developers of the code of the different programs to identify the data structures corresponding to tasks. And could you walk us a little bit more through this manual process that those developers have to go through for identifying, of the suggested data structures, which is the right one to use, and how we can help developers identify those?
Okay. So with suggested data structures, there are multiple ways to verify this. The first one is actually you can use application logs. Application logs usually will have high-level data structures, and you can just check with the log to see if it's the correct one or not. And the other one is the existing test cases in the program. For Firefox, and then many open source programs, they actually have the unit test. You can leverage such tests and then try to determine if this is the correct one or not. Because I think verification is, in this case, is simpler than finding them. So.
Great. If there are no more questions, let's thank Shiqing again for his talk, and again congratulate him and his co-authors for the Distinguished Paper Award.